Hello there. This is the beginning of our next module dealing with probability and probability distributions. So a sample is not identical to the population from which it was selected, right? A sample is a subset, so it's not going to be the same thing. And so any quantities you compute from the sample, like the sample mean, that's x bar, or the sample standard deviation S, or a sample proportion, we could use the notation p hat. It represents the corresponding, we want to know something about how well these statistics represent their corresponding population values. In other words, how well does x bar estimate mu? How well does S estimate sigma? Okay, so it turns out for us, probability gives us a way to measure our accuracy. Now probability, we could have a whole course in probability. In fact, we do here. And it can be taught from a very mathematical perspective. For this applied statistics course, we're just going to look at enough probability to get us the kind of foundation we need to do the statistics that we want to do. Okay, so first we're going to look at some foundational terms. A random experiment, sometimes just called an experiment, is a process that results in exactly one of a well-defined set of observable outcomes. So experiments result in outcomes. Now each of the outcomes cannot be predicted with certainty. So tossing a six-sided die is an experiment. Tossing a coin is an experiment. Checking to see if a person has a particular disease from a diagnostic tool, that's an experiment. We don't know what's going to happen, and so that makes it a random experiment. Now, the sample space is the set of all possible outcomes of an experiment, and we usually denote this with the letter S. An event, next definition here, is any subset of the sample space. That is, it's any collection of outcomes from an experiment. And so if we are tossing a six-sided die, then the sample space would be the numbers 1 through 6, and one possible event would be to toss an odd, and that would be the outcomes 1, 3, 5. Okay, so these three terms are important. Of interest in probability theory is computing the probability of some event. What is the chance, we often say, or what is the probability that some event will occur? Okay, so when we get that computation, and we'll get to that point in a little bit, how do we interpret it? So for example, if somebody says the chance of observing a head on a coin flip is 0.5, what does the 0.5 mean? Or what does the 1/2 mean? We're going to look at 4 different interpretations for probability. This first one here, a classical interpretation of probability, and it's an interpretation that arose from games of chance, in particular gambling games. Much of the theory of probability has its roots in gambling games. But a few things with this, or the main thing with this rather than a couple of examples, is that the chance of an event E under the classical interpretation is computed by using the number of outcomes favorable to the event E, and we use the notation capital N subscript E, divided by the number of possible outcomes, capital N. And if you recall, capital N here, the way it's phrased, is the number of outcomes in our sample space. And this is the number of outcomes in event E. Okay, that's an E there. Now, a couple of examples here. So suppose we flip a coin. So flipping the coin is the experiment. All right, and that results in this sample space. We could see a head or a tail. All right. Now, what's the probability of a head? Well, probability of a head, according to this interpretation, it says it's the number of outcomes in that event divided by the total number of outcomes in the sample space. Well, there's 2 outcomes in the sample space, and there's H is we could think of it as a simple event because it's just a singular outcome here, so it's 1/2. All right, so that's how we think of the probability of a heads under the classical interpretation. Another example here, the probability of drawing an ace from a deck of cards is 4 out of 52. What are we getting at here? What's the sample space for drawing a card out of a deck of cards? So the experiment is to actually draw a card. The sample space would be, so you'd have your 2 of hearts, 3 of hearts, and so forth up to the ace of hearts. Then you'd have your diamonds, then your clubs. I'm not going to write all that out here. And then your spades, so you'll have, say, your 2 of spades up to the ace of spades. All right. And so if we want to know something about, this is just an artificial line there, the probability of seeing an ace, the ace is the event, and the number of outcomes that correspond to that is 4, right? There's 4 aces. There's an ace of hearts, ace of diamonds, ace of clubs, and ace of spades. So it's 4 out of 52 cards in a deck. Okay. Now, one thing that is key, or that is critical for this interpretation to be appropriate, is that all outcomes must be equally likely. So the appropriateness of this kind of interpretation depends on that assumption, that all outcomes are equally likely. Now, in flipping a coin, that's a reasonable assumption. In drawing a card from a deck, that's a reasonable assumption. But there are experiments where that is not a reasonable assumption. For example, if we're considering a rare disease and a person either has it or they don't, and if it's a rare disease, then the chance of that person having it it wouldn't be appropriate to say that's 1/2, and the chance of them not having it is also 1/2. So this sort of interpretation depends on that kind of assumption, and you can see why this sort of interpretation arose from games of chance, because a lot of games of chance can be boiled down to a sample space where the outcomes are equally likely. Second interpretation, the relative frequency concept of probability is an empirical approach to probability based on the repetition of an experiment a large number of times. So if the experiment is conducted n different times, and if the event E occurs on little n sub e of these trials, then the probability of E under this interpretation is approximately n sub e divided by n. It's a relative frequency. Right? Frequency would just be the raw count. That would be n sub e. The relative frequency, because you're performing this experiment in different times, that makes it a relative frequency. Now you may look at this formula and you think, well, it looks a lot like this one here, but the difference is capital N here is the number of outcomes in the sample space, the number of possible outcomes from the experiment. N here is the number of times this experiment is repeated. All right, so If we can repeat this a large number of times, and we look at the relative frequency for which the event occurred, then we're going to think of that as our probability, the way we interpret it. Okay. This is appealing because it has this nice interpretation. We can look back in terms of an experiment to think about this sort of interpretation. Another interpretation is called the frequentist approach, and honestly it's sometimes called the classical approach. I know we had classical up here, but in other circles outside of our text you may hear somebody talk about the classical approach to probability, and they mean the frequentist approach or they may mean the frequentist approach. So the frequentist approach of the probability of some event is defined to be the limit of the observed relative frequency of that outcome. Really, that should be of that event, if the number of times the experiment is performed, and that increases without bounds. So here's coming back to this coin flip example. How do we define or interpret the probability of observing a head? So you may have a coin in your pocket, and if you do, take it out, flip it 10 times. So you're going to want to hit the pause button. But if you flipped it 10 times, you're going to get a proportion. Suppose I get 6 heads out of the 10 flips, so my proportion is 0.6. Now suppose I flip it 30 times, so flip it 20 more times, and if I flipped it 20 more times, now suppose I got 12 out of 30 for that first 30 flips. That proportion of heads is 0.4. Now this definition here says, let the number of times the experiment increase without bound. So I'm going to let the number of flips go to infinity, and whatever this number approaches, that's what we think of as the probability of a head. So this here is the probability of seeing a head on the flip. Now if you could imagine what would happen as you flip this, as you increase the number of flips, this number is going to change. 0.6 to 0.4, then it's going to change again, and as the number of flips gets really large, the changes are very small, and so this is going to converge to some number, and that number we think of as the probability of the head. It's a limit idea. That's the frequentist approach to interpreting probability. Last approach here, the personal approach, or the subjective probability approach. There are situations in which it's difficult to imagine the repetition of an experiment, and that's what we needed for the previous two interpretations. So in these cases, what we might do is we might make a one-shot statement of belief regarding the likelihood of an event. So for example, the football game that's going to happen this weekend, or suppose one that's going to happen this weekend, the chance that SFA wins, that game with that particular team is not an experiment that will ever be produced again, because the players are different time of season and so forth. But because of that, we can think of that as a one-shot sort of experiment, and so we can make a statement about the probability that SFA will win. If we say it's 0.65, that's based maybe not so much on empirical evidence, but on a belief about what's going to happen this weekend. Okay, I shouldn't say it's not based on empirical evidence. It's not based on evidence from the repetition of some experiment. Now, unfortunately, subjective probabilities can vary from person to person and cannot be verified empirically. Okay, and that goes back to the idea that the experiment cannot be repeated, so we have trouble with this this interpretation. That said, this sort of interpretation has its place in a particular view of statistics called the Bayesian, a Bayesian view of statistics. We won't get into that for our class, but you should be aware of it. For our class and really our textbook, we most often will use the frequentist approach to interpreting probability.